Hey kiddos, today we're going to be talking about trapezoids and kites. So these are the final quadrilaterals that we're going to be discussing. So let's start with the trapezoid. It is a quadrilateral, 4 sides, with exactly one pair of sides being parallel. Okay, so the bases, top base, bottom base, those 2 sides are the ones that are going to be parallel. The base angles of a trapezoid, base angles, are 2 consecutive angles whose common side is a base. A trapezoid has 2 pairs of base angles. In trapezoid ABCD, angle A and angle D are one pair of base angles, and angle B and angle C are the second pair. The non-parallel sides are called legs. Now, we do have a little special type of isosceles if the legs of a trapezoid end up being congruent. So as you can see here, these are congruent. Then we call this an isosceles trapezoid. So, and to take that a little bit further, isosceles trapezoids have something unique about their base angles then. So if a trapezoid is an isosceles, then each pair of base angles is congruent. So the 2 base angles at the bottom would be congruent to each other, and then the 2 base angles at the top would be congruent to each other. Isosceles trapezoid base angles converse states that if a trapezoid has a pair of congruent base angles, then it can be deemed as an isosceles trapezoid, because then we would have to justify that angle B and angle C would also then be congruent. All right, so now let's look at the diagonal that can be drawn in an isosceles trapezoid. A trapezoid is isosceles if and only if its diagonals, are congruent. So as you can see here, the diagonal AC and the diagonal BD are actually going to be classified as being congruent to each other. And we do have a special formula that we will be using for trapezoid, and that's being able to find the mid-segment. So the mid-segment is a segment that connects the midpoints of its leg. So obviously if it's a midpoint, connects the midpoints of its legs, that means it bisects the legs into 2 congruent pieces. All right? And here is what our formula is. It is basically 1/2, so half of the top base plus the bottom base will equal your midsegment. Okay, or you can write it in another way: AB plus CD, and then just divide by 2 if you don't like dealing with the multiplying by 1/2. And now for our next shape, the kite. A kite is a quadrilateral that has 2 pairs of consecutive congruent sides. Opposite sides are not congruent, and the congruent angles of a kite are formed by non-congruent adjacent sides. So this is typically what our kites will look like. So notice the adjacent sides here. These 2 are going to be congruent to each other, and then these 2 would be congruent to each other. Kite diagonals theorem states that if a quadrilateral is a kite, then its diagonals are perpendicular. So if you look at line segment AC and line segment BD, we can see that these 2 diagonals are perpendicular to one another, which justifies why this is a kite. We also have kite opposite angles theorem. So if a quadrilateral is a kite, then exactly only one pair of opposite angles are congruent. So in this case, we would have that angle A would be congruent to angle C. I know that angle B and angle D are opposite, but there's only one pair of opposite angles being congruent, and that is only these 2 right here. So, identifying special quadrilaterals. Each shape in the diagram has the properties of shapes linked above it. For example, a rhombus has the properties of a parallelogram and a quadrilateral. this refers back to that, what do you call it, family tree that we made. So these are all quadrilaterals, okay? And then from the quadrilateral family, we can break down into 3 separate groups: parallelogram, the trapezoid, and the kite. Parallelograms can be broken down into the rectangle and the rhombus, and then the rectangle and the rhombus can be broken down into a square. So remember, technically, a square can be a rectangle and be called a rhombus, okay? The trapezoid, the only one that it breaks down further to is the isosceles trapezoid, and the kite is all on its own. All right, so let's get started on this first example. We're going to prove that ABCD is a trapezoid, and then we're going to decide whether it's actually an isosceles trapezoid. So in order to discover if it's a trapezoid, what we're first looking for is that it has to have 2 sides, 2 opposite sides that are parallel to one another. So in this case, that means that they have to have the same slope. So we need one pair of opposite sides to have the same slope. So let's look for our first slope from A to B. So remember, we always rise over run. So from A, I'm going to go up 1, 2, 3, 4. And I'm going to go to the right 2. That's positive 4 over positive 2, which reduces to 2. All right, now let's look at the next slope from BC. So I'm going to start actually at C. I want to rise. I'm going to go up 1. And then I'm going to go to the left 1, 2, 3. Which that's a positive 1 over a negative 3, which is simply just negative 1/3. All right, next one from C to D. Start at D. We're going to rise up 1, 2, 3, 4. Hold on, I can't count. 1, 2, 3, 4, 5. I did count, right. We went up 5, and then we went to the left 1. So that is a positive 5 over negative 1, which reduces to negative 5. And so far, as you can see, none of our slopes are matching up. So right now, this doesn't look like it's a trapezoid. But let's look at that final one from A to D. All right, so from A to D, so I'm going to start at A, and I'm going to go down 2, down 2, and I'm going to go to the right 1, 2, 3, 4, 5, 6, right 6. So that's a negative 2 over a positive 6, and that reduces to a negative 1/3. So finally, yes, we got 2 slopes that actually are the same. So that means we got 2 lines that are parallel, but the kicker here is they have to be opposite of each other. And BC is opposite of AD. So far, so good. We know that these 2 sides are parallel. So yeah, it is a trapezoid. Now, let's figure out if it's an isosceles trapezoid. Now, in order for it to be an isosceles trapezoid, we know that it has to have congruent legs. So we're not worried about the base. Okay, the bases don't have to be congruent, but the legs do have to be congruent. So what we're going to figure out, or what we're going to use here, is Pythagorean theorem to help us figure out what that distance is. So I'm going to kind of draw in my right triangles here. So that's 1, 2, 3, 4, and that was 2. And then this one over here was a 5 and a 1. So I'm only going to look at my legs. So we're going to disregard here finding that distance and finding that distance. Okay, so making your life a little bit easier. So what we got here is for A to B, 4 squared plus 2 squared equals C squared. 16 plus 4 equals C squared. That's 20 equals C squared. To solve for C, you got to take the square root. And we're just going to leave our answer in radical form. So you end up with the radical of 20, square root of 20. Which, oh no, we can break that down to actually 2 square root of 5. So that actually does reduce to 2 square root of 5. All right, now let's look at CD. So that is 5 squared plus 1 squared equals C squared. 5 squared is 25 plus 1 squared is 1 equals C squared. You get 26 equals C squared. Take the square root of it. So square root of 26. Can you break down the square root of 26? 26 divided by 2 is 13. Can't break down 13. Nope, so it would be square root of 26. Now, clearly here, we can see that these answers don't match up. They're not the same. So that tells me that the distance from A to B is not congruent to the distance from D to C. So, no. Why? Because the legs are not congruent. All right, kiddos, so let's go ahead and put our properties to use here on our next example. So we have the stone above the arch in the diagram is an isosceles trapezoid. So we need to find the measurements of angle K, J, and M. All right, we're going to explain our reasonings here as well. So they've given us that the angle L is 85 degrees. Now, one of the properties that we need to recall about isosceles is that their base angles are, lucky for us, congruent. So, therefore, if angle L is 85 degrees, and angle K has to also be 85 degrees. And we know that angle J and angle M will also have to be the same. This is where you have to use some prior knowledge here. We should hopefully recall that the total interior sum of a quadrilateral is 360 degrees. So if I know that and I take away the 85 and the 85 that I already have, that means I'm left with 190 degrees left over. Now I know that these two angles here are equal, they're the same, so all I have to do to that 190 is divide that by 2, and I get 95 degrees. So we can then state that angle J is 95 degrees and angle M is 95 degrees. J, 95 degrees. K was the 85 degrees, and M, 95 degrees. The reason why is because base angles are congruent. All right, so our next example here states that if EG is equal to FH, so that means EG, oh, that's this diagonal, is congruent or equal to FH, which is the other diagonal, is this trapezoid an isosceles one? Well, if you know your properties, then you know that this answer is a yes. Okay, our reasoning is if the diagonals, ooh, that's bad spelling. Diagonals are in fact congruent, which in this case, because of that, they're telling us they are, then the trapezoid is an isosceles one. All right, moving on to number 4. If measurement of angle HEF, so if this angle is 70 degrees and angle FGH is 110 degrees, is this trapezoid an isosceles? All right, so we're going to have to use our knowledge about having two parallel lines cut by a transversal. And what we see here is if you have two lines that are parallel cut by a transversal, and we see the location of these two angles, my 70 degrees, and notice I labeled this angle as y degrees, they are consecutive interior, which means that they are supposed to be supplementary. So, if that's true, we can figure out what y degrees is. So basically, 70 plus y degrees is supposed to be equal to 180 because they're supposed to be supplementary. So subtract 70 both sides, we get that y equals 110 degrees. All right, now looking for the other angle over here, okay, we also see that this angle, the 110 degree angle, is consecutive interior to the x degree angle. So we know that they're supposed to add up again to 180. So let's mathematically work that out. So we have 110 plus the x degree equals 180. Subtract 110 to both sides. And we get that the answer is x equals 70 degrees. Now, in making this observation, we clearly see that these two base angles are congruent, and we see that these two base angles are congruent. So therefore, we can justify that, yes, this is an isosceles trapezoid because base angles are congruent. So our next problem is actually using the mid-segment formula. So notice I kind of rewrote it here because the previous problem when I talked about it, we had letters involved. So here's a more straight to it formula. And it's base 1 plus base 2 divided by 2 gives you your mid-segment, okay? So in this case, it's PQ plus SR divided by 2. So if I plug that in, PQ, according to here, is 12, plus SR is 28, and I would divide that by 2. 12 plus 28 is 40, 40 over 2, so 40 divided by 2 is 20. So we would know that MN is 20 inches. All right, our next example states, in trapezoid JKLM, angle J and angle M are right triangles. So notice you have to follow the order of the letters here. So I couldn't make it JMLK. So I had to go in this direction to label it JKLM because J and M had to be at the ends here. Okay. So JK is 9 centimeters. The length of the mid segment, which I just drew in, is N to P, and that is 12 centimeters. You don't have to use a ruler unless you want to, but I've already kind of sketched it out for you, and we're going to figure out what ML is. So, in this formula, which we're using the mid-segment formula, we know only one of the bases, we don't know the other. So, what we would have here is that base 1 is going to be x, plus base 2, which is 9, divided by 2, we know is going to equal what the mid-segment is, and that is 12. So if I work this out, multiply 2 to both sides, we get x plus 9 equals 24. Then I got to subtract 9 to both sides, and we get that x equals, if I'm not mistaken, I believe we get 15. So we just discovered that ML has to be 15 centimeters. Now there's another way to think of this. You can think of it as from 9 to get to 12 is 3. So from 12 to get to what ML is would have to also be the same distance in a sense. Also 3. So there's another way to think about it as well. All right, it's about time we're going to talk about a kite. So let's look at our kite. Find and measure angles in kites. Find the measurement of angle D in a kite shown below. So we can see that DE is congruent to EF and DG is congruent to FG. Okay, so we know that if we were to draw a diagonals here, these would be perpendicular, just kind of going over these properties. And we also hopefully recall that these opposite angles are congruent. So I'm going to label that as an X, and I'm going to label that as an X because I know they're going to be the same. So recalling the total sum of a quadrilateral is 360. So if we add these all up, we have to add them and make them equal to 360. So I have 2x, x plus x is 2x, plus the 115 plus the 73 has to equal 360. Let me combine those terms. So 115 plus the 73 is 188 equals 360, right? I'm going to subtract that 188. We get 2x equals 172. Last step here is to divide by 2, and we get that x equals 86. So one of the angles is 86 degrees, and the other one would be also 86 degrees. All right, moving on to our next example about a kite. In a kite, the measure of the angles are 3x, 75, 90, and 120 degrees. Find the value of x. What are the measures of the angles that are going to be congruent? Because we know that one pair should be congruent. Show all work. All right, so notice I know that a kite is a quadrilateral, has a total interior sum of 360. So I'm going to take these four angles and we're going to add them up, and we would get 3x plus 285 when I combine those like terms equal to 360. I'm going to subtract that 285 to both sides, and we get that 3x equals 75. Last step is going to be to divide by 3, and x equals 25. So to figure out which angles are the congruent one, I'm going to work with that right there, which is 3x, which is 3 times 25, which is 75. And if I'm not mistaken, we have one angle that's 75 degrees, and we have this other one that's also 75 degrees. So that would be our congruent pair. All right, so next problem, identifying a quadrilateral. So what is the most specific name for this quadrilateral that we can give? So basically, besides quadrilateral, can we name it as a trapezoid, kite, or parallelogram? If we decide it's a parallelogram, then can we name it a rhombus or a rectangle? And then if we can classify it that, could we actually go the farthest by classifying it as a square? So let's look. We got ABCD here looks like a square, but you must rely only on marked information when we interpret this, okay? So one thing I do see is that we have that diagonals bisect each other. So I'm going to write that. Diagonals bisect each other, which I know is a property of a parallelogram. So right now I know it's a parallelogram. That's all I got. So all I can say is that this is a parallelogram. I can't go any further. The reason why we can't go any further is because there's no more information given about the side lengths. I don't know anything else about the side lengths. And I don't know anything about these angle measurements. So I can't determine further if it could be a rectangle, rhombus, or a square. So all I got is that it's a parallelogram. All right, next example, 10 here says that quadrilateral DEFG has at least one pair of opposite sides congruent. So what are the different types of quadrilaterals that meet this condition? All right, so let's talk about the most recent, which is a kite. And that rule doesn't apply to a kite, so that's not right. So what about a trapezoid? Trapezoid, no, their opposite sides aren't congruent, so no, that doesn't work. So we do have then a parallelogram, which that is true for, which therefore means that it's also true for a rectangle, which would mean that it's also true for a rhombus, and of course, the square. And there's actually one more. The trapezoid breaks down further to an isosceles trapezoid, which then, yes, justifies the rule of one pair of opposite sides being congruent. So the isosceles trapezoid would be our final answer. So there are 5 quadrilaterals that meet that one condition. Now, as you can see here, this last problems, I want you guys to handle them on your own. All 3, A, B, and C. Make sure you give reasons. Tell me which type of quadrilateral can it be. All right. Ciao.